2,000 tons of cryogenic fuel. 2 giant ships at a speed of 28,000 kilometers per hour. Docking in outer space without the right to make a mistake. If something goes wrong, the explosion will be visible from Earth with the naked eye. This is not a scene from a movie. That's what SpaceX plans to do in 2026. And without this, humanity will never get to Mars. Not because there is not enough money. Not because there is no political will. Because physics leaves no choice. No rocket in history can carry enough fuel to fly to Mars in a single launch with a full load. This is a fundamental limitation. It is called the tyranny of the rocket equation. And the only way to get around it is to refuel right in orbit. That's why what SpaceX is going to do this year is more important than any other event in space exploration in the past decade. More important than Metazillah's capture of the rocket. More important than Starship's first orbital flight. This is not just a technical test. This is a test of the entire concept of interplanetary flight. If possible, the road to Mars is open. If not, the colonization program is pushed back for years. Let's take everything in order. Let's start with why this is necessary at all. And why it is so dangerous. Tsiolkovsky's rocket equation was formulated back in the year 1897. Its essence is simple and merciless. The farther you want to fly, the more fuel you need. The more fuel you take, the heavier the rocket. The heavier the rocket, the more fuel is needed to lift that fuel. A vicious circle from which there is no easy way out. In practice, this means the following: to deliver 1 kilogram to low Earth orbit, you need to burn about 20 kilograms of fuel at launch. To send the same kilogram to the Moon, the ratio gets worse. In order to fly to Mars with a landing and the opportunity to return, the numbers become astronomical in the literal and figurative sense. Starship in the basic configuration starts with a mass of about 5,000 tons. Of these, about 4,800 tons is fuel. The payload to low orbit is about 150 tons in a reusable version. When Starship reaches orbit, there is almost nothing left in the tanks. It will be enough for small maneuvers to correct the orbit, but not for an interplanetary flight. To steer Starship toward the Moon, it needs to accelerate to about 11 kilometers per second instead of the orbital 8. This is a huge amount of additional fuel. Fuel that it does not have after rising from Earth. For a flight to Mars, the situation is even more dramatic. A so-called trans-Martian impulse is needed. Acceleration for a few minutes. And so much fuel is required that a single start physically does not provide the necessary supply. The solution to this problem has existed for a long time. Theoretically, if you can't take all the fuel when starting from the surface, you need to refuel already in orbit. Launch a separate tanker ship that will lift fuel. Dock it with a traveler ship. Pump fuel. And only then fly to the goal. Sounds logical. But the devil is in the details. According to SpaceX's calculations, one Starship flight to Mars with a full load will require 8 to 12 tanker flights into orbit. Each tanker is a separate full-fledged launch of Starship. For one Martian expedition, you need to perform 9 or 13 launches in total. At the same time, the fuel must be pumped quickly because cryogenic liquids are constantly evaporating. Liquid oxygen boils at -183 degrees Celsius. Liquid methane at -161. In outer space without gravity, these liquids behave absolutely unusually. They don't flow down. They do not settle to the bottom of the tank. They float in bubbles, foaming. They create gas pockets where they should not be. Now let's talk about what exactly the docking will look like. The two Starship ships will approach each other stern to stern, engines to each other. It looks strange, but it is dictated by the design. Refueling ports are located at the top of the ship, next to the engines. It is easier to pump fuel through the upper part, closer to the engine compartment. Therefore, ships will have to come tail to tail. This requires special precision, because the engines of both ships will be dangerously close to each other during the docking process. The process itself looks like this. The Starship tanker enters orbit just below the orbit of the recipient ship. The receiving ship is already waiting. The tanker is slowly rising and approaching. At a distance of several kilometers, precision guidance systems are turned on. Laser rangefinders, computer vision systems. Ships align along the axis. The tanker is approaching literally centimeter by centimeter in the last meters. The docking mechanisms are connected. They are fixed. And only after that pumping begins. But the problem of weightlessness does not disappear anywhere. In the conditions of orbital flight, there is no top and bottom. Fuel in the tanks is a cloud of liquid that needs to be driven to the intake pipe of the pump. To do this, SpaceX has developed several approaches. The first is the method of sedimentation of fuel through acceleration. One of the tanker's engines is turned on at minimum thrust. This creates a tiny acceleration, about 1/1000th of Earth's gravity. It is enough for the fuel to settle to the back of the tank, from where it can be pumped out. Sounds simple. But turning on the engine of one spacecraft during docking with another creates vibrations, loads, and thermal effects that need to be accurately calculated and controlled. The second approach is centrifugal acceleration. Both docked spacecraft begin to slowly rotate around a common axis. Centrifugal force works like artificial gravity and presses the fuel against the walls of the tanks. A more elegant solution, but it requires the docking port to withstand the torques from the rotation of two giant masses of fuel. Now about the fuel itself. Starship uses liquid methane as fuel and liquid oxygen as an oxidizer. The methane-oxygen scheme was chosen for several reasons. First, methane could theoretically be produced on Mars from atmospheric carbon dioxide and water ice through the Sabatier reaction. This makes it possible to create fuel for a return flight right on the red planet. Secondly, methane does not clog engines with carbon-carbon deposits as much as kerosene, which makes it easier to reuse. Thirdly, the specific impulse of methane-oxygen engines is higher than that of kerosene-oxygen engines. But this pair has features that make orbital pumping particularly difficult. Liquid oxygen is an exceptionally active substance. It keeps literally everything that can burn burning. Steel burns in liquid oxygen. Under certain conditions, water too. The slightest contamination, the slightest spark, the slightest blow can cause a reaction. In the vacuum of space, combustion behaves differently than on Earth. No convection. There are no air flows. Combustion will be spherical and unpredictable. At the same time, there are several hundred tons of liquid oxygen and several hundred tons of liquid methane around. The energy potential of such a mixture is comparable to a small tactical nuclear charge. That is why all connecting elements, pipelines, pumps and pumping valves must be absolutely reliable. No backlash. No vibrations. Without the slightest leaks. Each joint is sealed to such an extent that not a single molecule of methane meets liquid oxygen outside the combustion chamber of the engine. At the same time, the problem of evaporation is being solved. When liquid oxygen is heated, it turns into a gas, and the volume increases by about 800 times. A tank designed for liquid will not withstand such pressure. Therefore, there are always safety valves in cryogenic tanks that vent the resulting gas. This is called a boil-off. The longer the ship waits for the tanker in orbit, the more fuel evaporates. The whole refueling process should be as fast as possible. Every hour of delay means tons of oxygen lost. SpaceX is working on solving the boil-off from several angles. The first is to improve the thermal insulation of the tanks. The better the tank is insulated, the slower the fuel heats up. But thermal insulation adds mass. And the mass is the main enemy of the Rocketeer. We have to look for a balance. The second is active cooling. The evaporated gas is not ejected, but is driven through the refrigerating machine, cooled back to a liquid state and returned to the tank. This is called vapor liquefaction. Technology exists on Earth. It is much more difficult to implement it in space on the required scale. The history of orbital docking is more than 60 years old. The first docking in history was performed by American astronauts Neil Armstrong and David Scott on the Gemini 8 spacecraft in March 1966. They docked with the unmanned target missile Agena. The docking was successful. But then one of Gemini's engines got stuck in the switched-on position and the ship began to rotate at a speed that threatened the crew with loss of consciousness. Armstrong decided to undock and stabilize the ship with difficulty. This was the first orbital emergency in history, from which they got out only thanks to the skill of the pilot. The Soviet docking program developed in parallel. The first automatic docking in the world was performed by the Soviet unmanned spacecraft Cosmos 188 and Cosmos 186 in October 1967. Since then, Soviet and Russian designers have accumulated vast experience in the field of automatic docking, which formed the basis of the systems used on the ISS to this day. But all these are dockings of light ships. The Union weighs about 7 tons. Progress is about 7 tons. Dragons are about 12 tons. Starship is a different world. At the time of docking, the total mass of the two spacecraft can be 1,000 or more tons. This is the mass of a small destroyer. Docking two objects of such mass in orbit is a completely new engineering task. And the accuracy here is much higher than for docking manned spacecraft with a transfer hatch. 2 astronauts can squeeze through the hatch even if the ship's docked with a slight angular deviation. But the filling pipes must match almost perfectly. Otherwise, when pressure is applied, the connection will be destroyed. Otherwise, cracks will appear during vibrations during pumping. Otherwise, a leak will begin. And the leakage of liquid oxygen or methane in outer space is a direct path to disaster. In addition to mechanical accuracy, there is a thermal problem. Cryogenic pipelines cause sharp cooling when in contact with conventional metal structures. The metal becomes brittle. Joints that work great at room temperature can burst from shock load at -180. All components of the pumping system must be made of special cryogenic grades of steel or aluminum alloys that retain ductility at extremely low temperatures. If you look at NASA's Artemis program, Starship's orbital refueling is an absolutely key element there. NASA selected Starship as the lunar lander. This means that people will fly to the moon again on Starship. But in order for Starship to get to the moon, he needs to refuel in orbit. Without this stage, the lunar mission simply will not take place. NASA paid SpaceX nearly $3 billion to develop a lunar version of Starship under the first contract and added about $1 billion more under subsequent agreements. All this money assumes that SpaceX will solve the problem of orbital refueling. That is why 2026 is such a critical year. This is not just a technical experiment. This is a test of the entire architecture of future lunar and Martian missions. There are competitors in this area, but they are far behind. United Launch Alliance is developing the Vulcan Centaur rocket, which in the future can also use an orbital depot. But we are talking about a much smaller scale. Blue Origin works on New Glenn and Blue Moon's moon lander. But in terms of the pace of development and the number of real flights, they are significantly inferior to SpaceX. The Chinese space program is developing rapidly, but orbital refueling on such a scale is also still in their plans, not in reality. This means that if SpaceX copes with the task in 2026, they will gain a technological advantage that will determine the development of space exploration for decades to come. The ability to refuel ships in orbit is not just one technical trick. This is an architectural solution that changes everything. Any point in the solar system becomes reachable if there are enough tankers. Payload size is no longer limited by the capabilities of a single launch. This is the end of an era when each mission must fit into one missile. Think about it this way. To send enough cargo to Mars to establish the first base, dozens of separate missions are needed. Each is independent. Each is optimized for its task. This means a huge duplication of equipment, complex logistics, and astronomical costs. With orbital refueling, the picture changes. One large spacecraft takes the maximum cargo from Earth, refuels in orbit, and goes to Mars with full tanks. Then he returns, refuels again, and flies again. Not a one-time expedition. The beginning of regular cargo traffic between the planets. This is what Musk is talking about when he describes his vision of a Martian colony. He is not talking about heroic single flights, but about a fleet of ships that ply between Earth and Mars like cargo ships between ports. Every 2 years, when the Earth and Mars approach each other at a minimum distance, the launch window opens. It lasts for several weeks. At this time, you need to send as many ships as possible. The more ships, the more people and cargo will get to Mars. The more people and cargo, the faster the colony grows. This is simple and cruel logistics. The Raptor engines used in Starship are an outstanding achievement in their own right. They operate on a full-stroke afterburning cycle, where both the fuel and the oxidizer are preheated in the pre-chambers before entering the main combustion chamber. The pressure in the combustion chamber is about 300 atmospheres. This is a world record for production engines. The specific impulse of the Raptor in a vacuum is about 380 seconds. Falcon 9's first stage engines give about 282 seconds at the surface. The Raptor uses fuel much more efficiently. During orbital refueling, the tanker's engines can be used to create that very small acceleration for the fuel sediment. The Raptor knows how to throttle the thrust from about 40 to 100%. When refueling, you need to work at the lowest possible thrust, literally a few percent, in order to create the correct acceleration without dangerous vibrations. After working out the docking, the next step will be to create an orbital depot. A specialized version of the Starship without main engines, designed exclusively for fuel storage and transfer. Such a depot is constantly in orbit. It is regularly replenished by tankers from Earth. Ships going to the Moon or Mars dock with the depot, refuel and fly on. This is much more convenient than waiting for a specially launched tanker every time. Fly up. Refuel. Fly. The concept of an orbital depot is not new. It was developed back in the 60s of the last century. But then she ran into the boil-off problem. Without active cooling, cryogenic fuel evaporated too quickly for storage and orbit to be practically profitable. Now technology has moved forward. New insulation materials, compact refrigeration machines, new control systems. SpaceX claims to have solved the boil-off problem enough to make the orbital depot a reality. As of the beginning of 2026, SpaceX had already completed several successful orbital flights of Starship. The ship returned to the launch pad and was caught by the turret's manipulators. The thermal protection system for re-entry into the atmosphere has been worked out. The third-generation Raptor engines demonstrate reliability that is significantly superior to earlier versions. The next logical step is orbital docking. SpaceX has officially designated this as a priority for the current year. There is a fair opinion that SpaceX is too optimistic in its time estimates. This is an honest observation. The company regularly named the deadlines, which were then shifted. Starship's first manned flight to the Moon was postponed several times. Orbital tests also took place later than announced. But another indicator is important. SpaceX is really moving forward. Let it be slower than promised. Let it be with accidents and explosions. But it moves. Each explosion of the test prototype in Boca Chica brought data that made the next prototype better. Each failure turned into knowledge. Remember the story of Falcon 9. The first launches were unsuccessful. The landing of the first stage seemed fantastic. Now the landing of the first stage of the Falcon 9 is a routine. It has almost ceased to be shown in live broadcasts because it happens so predictably that it is not of news interest. Starship is now in roughly the same place where Falcon 9 was in 2013. It's still a long way from the ordinary. But the direction is obvious. Imagine how it will look visually when everything works out for the first time. 2 silver cylinders 50 meters high. Each is the size of a small skyscraper. They are slowly approaching in absolute silence against the background of black space and the blue globe of the Earth. One unfolds. Tail to tail. The engines look at each other. The distance is shortening. Meter. Half a meter. 10 centimeters. Docking. Fixation. And then the quiet, invisible, incredibly important work begins. Hundreds of tons of liquid cold flow from one ship to another. Without this moment, everything else is meaningless. The Moon remains a dream. Mars remains a point in the sky. That is why 2026 is not just another year in the history of SpaceX. This is the year when humanity will either take the next step towards becoming a multiplanetary species, or make sure that this step requires even more work. In any case, the result of these tests will change the understanding of what is possible.